Hi everyone, I'm Dan at the University of Manchester. So here is my Twitter handle if you want to use that to ask me any questions or give me any feedback or comments on the talk. I'm going to be talking about sort of model-independent modified gravity based on this work which was published in PRD. So just for anyone who thinks my title is a bit crazy, so a red herring is an idiom in English. It basically means something that's a distraction. So that's sort of the explanation of my title. And then before we proceed, I just wanted to make sure we're all on the same page about what the Poisson equation is and kind of how it works, because it will come up a lot during the talk. So I've got the Poisson equation here. And so we just mean schematically something that has a gravitational potential, that has the Laplacian of that gravitational potential, so that the second spatial derivative that becomes a k squared in Fourier space. And then that is proportional to basically the density. Okay, and that's what I mean by the Poisson equation. So bear that in mind as we go through. So I'm going to start by sort of just giving some motivation, why modified gravity and why model-independent modified gravity. And what I'm going to do, because there's going to be discussion sessions for all these talks, I'm going to try and use those motivation to provoke observers and theorists a little bit. And then hopefully people will turn up and we can have a good discussion. So then about halfway through, I'll sort of have the punchline or the kind of key result. And then I'm going to go into some of the physical reasoning. Okay, so I'm not going to go too technical here, but just some of the physical reasoning behind the result and how it's arrived, and just to help develop some intuition. And then finally, I'll just have some closing remarks. Okie dokie, so model-independent modified gravity, why? So firstly, why modified gravity? Well, for me, just the fact that it's not ruled out. So if you want to sort of think about motivations for why it might be useful to us, obviously you've got the dark sector, so you've got dark matter and dark energy, for which we only have gravitational evidence. We've then got sort of a bunch of crises or problems that won't go away. So, we still haven't found WIMPs, which are a particular dark matter candidate. The cosmological constant problem has, again, hung around for a long time and not gone anywhere. We've got some recent tensions in cosmology. So we've got the Hubble tension and things like sigma 8 and stuff like this. And then I think another motivation for just considering modified gravity in general is quantum gravity. So general relativity, Einstein's GR, we expect this to break down. And I think really the question is on what scales and energy scales and times and whatever does it break down. So maybe the limit we're dealing with as cosmology isn't exactly general relativity, but it's actually slightly different. And it's just good at testing theories in every regime we can. So hopefully that convinces you that modified gravity is worth thinking about. But what about model-independent modified gravity? So this is the bit where I upset the theorists. I think none of the models that we really have at the moment are sort of well motivated. They're not really compelling. Okay. Related to that, we can't even be sure that the right answer is amongst the set we're looking at the moment. A lot of talk goes about the Horndeski model, but it's not really general. And then one of the things I like about model-independent ways of doing things is you get good null tests of sort of our standard cosmology. Okay. And then the final thing I wanted to mention is just that, we have this framework, this PPN, parameterized post-Newtonian framework in the solar system, which is a great way of testing all different theories of gravity in different ways. But we came up with that before we had any reason really to doubt GR in the solar system. Okay. So again, it's just kind of saying, look, we don't have to think these things will fail tests to make the test worth doing. And then just an aside for anyone that doesn't know it, the story of sort of Neptune and Vulcan is a really fascinating parable to go and read about. Okay, so hopefully I've convinced you that sort of model-independent modified gravity is really worth caring about and thinking about. So what's the state of play? Well, on the large scales in the universe, where we can use our linear perturbation theory because our fluctuations in the universe are small, we understand things really well. We understand modified gravity really well. And basically, it comes down to these two equations. So we've got this first equation, which is like a modified Poisson equation. Okay. So on the left-hand side, we've got our k squared and our gravitational potential, as we expect. this rho bar and delta essentially are the relativistic densities. So you can think of these two objects together as the density, and the point is just that the density definition becomes, you have to be a bit more careful on scales near the horizon, but basically these two terms represent the density. And then we've got our proportionality bit, and then we add in this mu to the Poisson equation, okay? And this mu, by giving it different functions of time and space, we can represent all sorts of different gravity theories and their effects on the universe. So we actually need a second equation as well, which is this equation here. So there are two scalar potentials in general relativity, but typically in the linear perturbative limit in most cases and in the Newtonian limit, these two are equal. But this isn't necessarily true in modified gravity. So we have this eta as well, which we also allow to be a function of time and space. And then that's our second equation. So these two equations pretty much describe modified gravity in a model-independent way on large scales in the universe. And this is well studied. Now, what we don't have is a sort of equivalent version of this that works on small scales, where the density contrast can become large, okay? So I should note there's sort of some cool work. You should go and check these papers out. They're really interesting papers. For me, they are a priori restricted to sort of certain parts of theory space. They don't deliver exactly what I'm looking for with this, model independence thing on small scales, but you should definitely go and read those papers anyway. They're very interesting. So what do people do on small scales if we don't have this model independent stuff? Well, they just sort of run n-body codes for specific models, which is very time consuming and is a lot of work, and you can only ever learn about one model at once. So we can learn that way, but it's a very slow and laborious process. Now, why am I going on about all of this? Well, I'm going on about all of this because future surveys, so Euclid, LST, insert your favorite upcoming cosmological survey here, are going to have the majority of their data on nonlinear scales. Okay. So I think this is a problem. I don't think this is just the elephant in the room. I think this is the whole savannah. So we're going to have all of this fancy data, and what we're saying is we can't use that data and all that effort to really say something definitive about modified gravity and of course dark energy in the universe. So I think really this is a problem and it's a waste, and we should do better than this. Now, sort of coming back towards my title, what about this Poisson equation? So this Poisson equation turns up in a lot of places. Okay? So is this a clue or is this a red herring? Right? Maybe this is the thing we can use to make a framework for modified gravity that can apply on all scales in the universe. And so the punchline is, actually, we can do exactly that, okay? So we have two equations here, and I'll get into their derivation a little bit in the second half of the talk, but basically the first one's something like a Poisson equation. So again, we've got k squared times gravitational potential on the left-hand side. On the right-hand side, this whole term here is that sort of relativistic version of the density, and we have our proportionality constant and our modified gravity effects, okay? And then here we have, the relationship between our two potentials with the modified gravity represented by the eta. And these equations actually apply on all scales, okay? The density contrast that's here, this density fluctuation isn't required to be small. And actually, you can use these to analyze and combine data from any surveys on any scales, okay? So that's the punchline. We can do this, we should do this. Now, the other sort of punchline in the paper is also an algorithm to determine whether a given modified gravity theory fits into this approach. Okay, and again, I'll mention that a bit towards the end of the talk. Okay. So something I should mention here is that these mu and eta functions here and here in these equations sweep a lot of complications under the carpet. And again, I'll come back to that. But that doesn't change the fact that these equations describe model-independent modified gravity on all scales in the universe. Okay, so very quickly, pause the video. Okay, right, good, on with the talk. So, gravity and cosmology, how do we normally study this? So I have this bar here which represents the whole universe. So on the right-hand side here is small scales. So there's some limit here below which, perhaps this is the solar system or the Earth. It doesn't make sense to think of things cosmologically. And then to the left-hand side, we've got the large scales, and in particular, some horizons. So this is sort of the size of our observable universe, okay? And then we have some nonlinear scales. So to the left of this nonlinear scale, the density fluctuations in the universe are small. and to the right on small scales, they are large. And that largeness is a problem. So we have this tool, this linear general relativity perturbation theory, which we use for a lot of our cosmological calculations. And this applies from the nonlinear scale upwards. Okay, so it works for all these regimes, but it can't work on scales smaller than the nonlinear scale. So on small scales, what we typically do is take the Newtonian limit of general relativity. So here I don't quite mean use Newtonian gravity, I mean take the Newtonian limit of the general relativistic equations. The distinction matters because it means you're still working in a fully relativistic framework that can handle volume effects and so on and so on. But that's what we do on small scales. Something that isn't really talked about is this possible intermediate regime here, where neither of these two limits apply. Okay, and I'll sort of mention that a bit more in a few slides, along with why we don't normally talk about it. But what we would ideally like is a single way of dealing with gravity, a single framework that applies on all of these scales, from the small scales all the way up to above the horizon signs. Now, in principle, we could use, full general relativistic calculations for this, but they're just too complicated and too difficult, so we can't do that. However, Marco Bruni, a student at Portsmouth, put out a paper in 2015 called the Post-Friedmann formalism, okay? And that actually gives you a tool that can be used to describe gravitational dynamics across all of these scales, okay? And so we're going to use that. Okay, so the Post-Friedmann formalism. So for those that are aware, this is a post-Newtonian-like expansion, okay, in powers of the speed of light. So a post-Newtonian expansion basically assigns each quantity some numbers of the speed of light, right? So a speed is 1 over the speed of light, a time derivative is 1 over the speed of light, a gravitational potential is 1 over the speed of light squared, and then we keep track of the numbers of speeds of light attached to everything in the equation, and that allows us to simplify the equations and see how all of the quantities work in this approximation, what they do. And in particular, the importance of this is that it doesn't require a small density contrast, okay? So the density fluctuations can be arbitrary. Okie dokie. Now, what's important about this is that it contains this large scale limit that we're used to using. That is contained with these, within these 1PF or first post-Friedmann equations. The small scale limit, the Newtonian limit that we use down here, is also contained within these 1PF, these first post-Friedmann equations. And actually, this possible more complicated intermediate regime is also contained within these equations. So this framework really does apply on all of these scales. However, if you have a look at the equations here, you can see that these are a bit ugly, right? These are a bit awful, really. You don't ever want to do a calculation with these equations. They're just too horrible. But it's possible to simplify them, okay? So in particular, what you can do is bundle a load of the extra rubbish that we don't want to deal with into this term here that I've called the 1 over c to the 4 nonlinear terms. And if you do that with these equations, what you're left with is something a lot like the Poisson equation. So you have k squared times the gravitational potential on the left-hand side, and you have the relativistic density term on the right-hand side, okay? So we have something that looks like the Poisson equation, but with some extra rubbish. We put all the extra rubbish into this term here. Now, why is this useful? At this point, we still can't use this. So let's consider what the universe is like at late time. So a standard lambda CDM universe with a cosmological constant, dark matter, and general relativity. So in that situation, we don't have an intermediate regime, okay? The Newtonian limit is valid all the way from small scales to above the nonlinear scale. And the linear theory, as usual, is valid from the nonlinear scale upwards. And then so you don't have any intermediate regime where neither of these two limits apply. Instead, you have an overlap where they both apply, and you can use either to do the calculations. So what this means is we can drop all these extra rubbish here that we don't want to deal with and just ignore them, okay? And I'll call this the simple 1PF equations, okay? And if you do this, you have something that applies on all of these scales that doesn't require the density fluctuations to be small All it requires is that there's no intermediate regime. And you can see that the equation is relatively simple. So I'll just reiterate that. If there is a good Newtonian limit on small scales and no intermediate regime, then gravity is described on all scales by this Poisson equation, which doesn't require a small density fluctuation. And of course, you have to add another equation representing the gravitational slip. Okay, so this is wonderful. This is exactly what we wanted. We have a framework to describe gravity on all scales, okay, that doesn't require the density contrast to be small. And what we can do is we can now look at these conditions, the good Newtonian limit on small scales and no intermediate regime, and we can turn these into a set of checks to apply to particular modified gravity theories. And that will tell us if those theories fit into this framework and would come under this model-independent approach. Okay, so a few technical bits here. The important things really are that your Newtonian limit and your perturbative limit kind of look the same in that region where they overlap, and that there is no intermediate regime, so they do overlap. That's sort of what 3 and 4 are telling you. And then in 5, this is really the difficult test, okay, which is that you need to check that the Newtonian approximation is a good description of your modified theory of gravity on all nonlinear scales, okay? And I don't know a way of doing this test without running an n-body simulation for that particular modified gravity theory yet. But any theories that satisfy all of these can be described by the parameterized simple 1PF Poisson equation and the slip equation, okay, on all scales in the universe. And in fact, these tests have been done, all 5 have been done for f of r gravity, and that does fit within this framework. Okay. So something I think that's interesting to think about is, what about a theory that doesn't satisfy these conditions? Well, the thing is, we know that lambda CDM is a pretty good description of the universe. And so a theory that doesn't satisfy these conditions isn't going to look a lot like lambda CDM. And so probably it's not a theory we need to worry about, right? Because we know that lambda CDM is a pretty good description of the observations that we have so far. Okay, so some closing remarks then. So you'll notice in the top right, I've killed off the fish, the red herring is dead. It turned out that the Poisson equation was a great clue. It was exactly the clue we needed. It wasn't a red herring. And we can use a Poisson equation combined with a slip equation, which is the ratio of the potentials, to analyze data on all scales from any survey, no matter how big the density fluctuation is. Okay, so something I alluded to earlier is that this mu and eta sweep a lot of complications under the carpet, okay? I sort of propose some possible functional forms for them in the paper, but you should just be aware that these aren't necessarily going to have simple forms, and they're sort of hiding a lot of, the complicated nonlinear dynamics now. Interestingly, Lucas Lombreiser's work, you can reinterpret in my framework as basically telling you how to calculate the mu and eta in this framework for known theories such as f of r gravity. Okay, so we actually know what these functions should look like to match f of r gravity. So how I think these things should be used is to do a pixel approach, right? So we do some grid in time and space, and you allow the mu and eta values in the grid points to just vary independently, and you just shove the data at it and say, okay, what constraints can I get on these things? And I think this is a really powerful null test for our standard cosmology. And it's really good, particularly if there's no deviation detected, or you might even be able to use it to find systematics. Where this falls down a little bit and where this isn't optimal is that if we do find a deviation, it's quite hard to backtrack to what kind of theory generated that deviation. But frankly, for me, if we find a deviation, I'll be so excited about it that I won't mind too much that this approach isn't completely optimal. And then the last thing I wanted to mention is that there's some simulation work ongoing with a PhD student at Manchester to explore some phenomenology. And I've got a quick plot here. So this paper I expect to be out in a couple of months probably. And basically what you've got here is, by allowing the mu function to have time dependence, you actually get different scale dependent behavior on nonlinear scales, which you can see from the different shapes of these curves. So on linear scales, all these curves match. And by changing where you turn or what times you turn the modified gravity on, you can actually get different scale dependence. You're getting scale dependence from time dependence. So I think this is going to be really interesting phenomenology to explore. Okay, thank you.